So I'm looking at the question today of whether or not mathematics is unreasonably effective. This comes from a paper by the Hungarian-American theoretical physicist Eugene Wigner. He received the Nobel Prize in Physics in 1963, but just before this, in 1960, he wrote this paper entitled The Unreasonable Effectiveness of Mathematics in the Natural Sciences, in which he claimed that the miracle of the appropriateness of the language of mathematics for the formulation of the laws of physics is a wonderful gift which we neither understand nor deserve. There are two main points that he makes in this paper, and it's the first of these that I want to focus upon today, namely that mathematical concepts turn up in entirely unexpected connections and often permit an unexpectedly accurate description of the phenomena in these connections. Or in other words, he thought it was surprising that mathematics was as useful as it is in describing the natural world, and that it could do so with the degree of accuracy that it can. He also made a second point, and in fact he says that the enormous usefulness of mathematics in the natural sciences is something bordering on the mysterious, and there is no rational explanation for it. He makes the second point to do with the uniqueness of mathematical models, but I won't deal with that here. So just to clear the ground, there are a number of interrelated ideas that I want to distinguish between and sort out, and it's only one of these that I'll be looking at today. So there's the idea that the universe is governed by laws of nature or natural laws, that those laws are consistently upheld throughout time and space, that those laws are discoverable or can be accurately approximated and comprehended by human minds, and lastly, the idea that mathematics is unreasonably effective in describing and predicting the behavior of the natural world. And so it's the last of these that I'll deal with. They're interrelated. I'll touch slightly on the penultimate one, but it's the last of these that will be the focus for today. So why am I talking to you at a Christians in Science conference about this question? Well, it's occurred to many theists, including Christian theists, that the unreasonable effectiveness of maths may have theistic implications. One way you might try and formulate this is by taking something like William Lane Craig's fine-tuning argument and reworking it slightly. So this is an argument with two premises and a conclusion. So premise one here would be that the unreasonable efficacy of mathematics and the natural science is due to either physical necessity, chance, or design. Premise two, that the unreasonable efficacy is not due to physical necessity or chance, with the conclusion that therefore it's due to design. Now, I haven't got time to go into premise two here, but it's premise one that I want to focus on. But of course, premise one presupposes that mathematics is indeed unreasonably effective. So we might want then to sort of unpack this a little bit in order to justify premise one with a similar syllogistic argument, with, again, two premises and a conclusion. So premise one here would be that for something to be unreasonably effective, it must satisfy some criteria, A, B, C. Premise four, that mathematics does indeed satisfy those criteria, A, B, C, whatever they might be, and therefore that mathematics is indeed unreasonably effective. And if you've justified that, then that can feed back into premise one of the first argument, giving you an argument for the existence of God. So I'm going to skip over that. So I want to, in the rest of this presentation, talk about then some of the types of mathematical description that are available and the grounds that we might have for deeming them to be unreasonably effective or not. So what kinds of mathematical description do we have? Well, the simplest case would be counting. A little bit more complex than this, we'd have arithmetic, so addition, subtraction, multiplication, addition. And then there are various kinds of models. We have, for example, phenomenological models, the simplest example of which would be curve fitting. So all we're trying to do with a phenomenological model is to reproduce the behavior that we see. We've got statistical models. I'm not a statistician, but this is quite similar in many ways to phenomenological models in the way I'm using the term here. So something like a normal distribution to capture the distributions of heights in a population. And then lastly, mechanistic models, by which I mean models that seek to capture the underlying mechanisms that govern the behavior of the universe and from which behaviors emerge that may or may not match with what we see in nature. So the question is then, how surprising is the efficacy of mathematics in each of those cases? Well, I'd argue for the cases of counting and arithmetic, it's hardly surprising at all that you might be able to number off, take your numbers and label them off to different objects in the universe, not very surprising. Similarly with arithmetic, particularly given that the axioms of the real numbers are chosen precisely to give us the sorts of rules of arithmetic that we experience in everyday life. Phenomenological models, similarly not that surprising, I would say, given the infinite flexibility of mathematics. For any series of data points you might have, you can find some mathematical function or set of parameters that will give you a fit to that data, and I would say something similarly for statistical models, though I'm not a statistician. If there is any hope, then, of mathematics being unreasonably effective, it seems to me it would be found within the realm of mechanistic models. Even there, though, there are going to be situations where I think for doubting the unreasonable efficacy of mathematics. And I'll go through a few of these now. So one of these would be in cases where you could reduce something that might look quite sophisticated at surface level, or certainly to a non-mathematician, to something which is a relatively intuitive example. So I take, for example, the incompressibility condition in fluid mechanics. Now that, to a non-mathematician at least, looks like quite an advanced concept because you've got a differential operator, a vector differential operator, you've got a velocity vector field. What it's saying is that if you have an elemental volume that's fixed in size, for this incompressibility condition, if a molecule of fluid goes in, then another one has to come out. But actually, that's nothing more sophisticated than balls in a bag that are drawn with replacement. If I take a ball out, 5 balls in a bag, I take one out, put one back in again, there's still 5 balls. Hardly surprising that maths is applicable for the balls in the bag, therefore hardly surprising that it's applicable for the incompressibility condition. It's just the same thing, but phrased in a more complex kind of way. There are other situations, I would argue, where, again, mechanistic modeling is not so surprising, or ways in which this is the case. One is in terms of the infinite flexibility of mathematics, both in terms of the equations that you have to choose from and the parameters that you can choose. An example of this would be von Neumann's elephant. He was supposed to have said that with 4 parameters I can fit an elephant, and with 5 I can make him wiggle his trunk. In fact, that was proven in 2010, so that's a 4-parameter model that gives you something that looks remarkably like an elephant. Similarly, if you've done some modeling yourself, you'll know that as you're making choices in model formulation, you begin to develop a sort of intuition such that you know if you choose a certain kind of term, you'll get a certain kind of behavior out at the end. And again, if you're doing that, which you can sort of not help but do to some extent, it's not so surprising if your model replicates the real world. Also, and entirely legitimately, you have to make modeling assumptions or simplifications. The real world's pretty hard to deal with, so you have to make it simpler to be tractable in some way. Sort of joke example of this is imagine a spherical cow. A cow has got a very complex geometry, but a sphere is simpler, so if you model a cow as a sphere, then that makes your life easier. And then one final example would be, maybe it's the case that we're focusing on mathematically tractable theories or data, so a good analogy here might be, well, maybe our tool is our hammer, our mathematical model is our hammer, and therefore we're only really interested in problems that look like nails. If we come across a screw or some other kind of thing in DIY, I don't know much about DIY, then we just don't really see it or are not interested in it. So it's hardly surprising we're only focusing on the nails. So let's go back to Wigner then. So what exactly was his line of argument? So he argued that, sorry, my piece of paper in the wrong one, that while concepts in elementary maths are formulated to describe entities which are directly suggested by the actual world, the same doesn't seem to be true of advanced concepts in physics, advanced concepts in maths, which play an important role in physics. So he says that in order to get more than a handful of interesting theorems, mathematicians have to define concepts which go beyond those contained in the axioms, our initial assumptions. And that those are defined with a view to allowing operations which appeal to our aesthetic sense, our sense of beauty, both in terms of the operations themselves, but also in terms of the results they can generate, both in terms of their generality and also simplicity. And he gives complex numbers as an example of this. Now, mathematicians, so historically the way this often works is that mathematicians will develop a concept first, and then later on, independently, physicists will independently construct the same mathematical concept for use with their physical theories. So note that it's not the case that the physicists trawled through the mathematical literature, found a piece of maths that was useful, and then applied it to their theory. Rather, a mathematician came up with it some years or decades before, then a physicist, in dealing with a piece of physics, realized they needed a piece of maths and then independently created it. So Wigner says, it wasn't inevitable that mathematical concepts chosen by physicists would have previously been conceived by mathematicians. So he gives again this example of complex numbers, and he says that complex numbers are far from natural and simple, that they can't be suggested by physical observations, and yet, he says, they're close to being a necessity in the formulation of the laws of quantum mechanics. The surprise then, says Wigner, is that the required mathematics is beautiful. But is that surprising? I mean, if you were to speak to a mathematician and ask them what is it that makes a piece of mathematics beautiful, they'd probably say something like patterns, symmetry, connections, consistency, simplicity, and generalizability. But aren't those exactly the sorts of things that would make a piece of mathematics useful in the first place? In which case, it's hardly that surprising that the things that are beautiful would be useful. Similarly, might it not be the case that we're biased as scientists or mathematicians in the theories or maths that we're willing to accept? Indeed, Wigner makes this point himself in his paper. He quotes from Einstein, who said that the only physical theories that we're willing to accept are the beautiful ones. However, even if beauty is not surprising, that doesn't explain the accuracy of the mathematical models. So, Wigner gives a couple of examples. I don't have time to go through them both here, so I'll just focus on the first, which is planetary motion. So he says that the law, he's referring in the case of this law to the F equals ma, forces mass times acceleration. He says it's simple only to the mathematically minded, this because the a here, the acceleration, is the second derivative of the displacement, and the second derivative is not intuitive to a non-mathematician. And yet, these laws have proved accurate beyond all reasonable expectations. He gives a similar example in quantum mechanics. So, a brief reminder, I was trying to, the point of this talk is to try to think about the question of whether or not mathematics is unreasonably effective, because it's required, if you want to make an argument for the existence of God, for premise number one here. So based then on our discussion so far, what conditions might we stipulate in order for a piece of mathematics to be considered to be unreasonably effective? Well, maybe it needs to make highly accurate predictions that have been verified by experiments. Perhaps it needs to be not obvious a priori that it should have been effective in a particular way. Or going even further, maybe there needs to be the existence of a priori reasons to doubt the efficacy. So, for example, if the modeling assumptions were not satisfied, and yet the model still turned out to be useful, or if there are previous pieces of experimental evidence or prevailing views that diverged from or contradicted the modeling predictions. It needs to be not unexpected purely due to an accident of history. That is to say, it shouldn't just be because the mathematicians thought of it first and the physicists later on that it's surprising. That wouldn't wouldn't really count. Similarly, maybe you came up with a piece of mathematics which applied in a certain area, and according to your initial assumptions, it shouldn't have applied in a second area, and yet it still made accurate predictions. Or maybe later on you find out that your initial assumptions as to the areas in which the equations were valid were unnecessarily restrictive, and again, that wouldn't therefore count as unexpected in this sense. It may be the case that the beauty of mathematics would be a reason for considering the efficacy of maths to be surprising, or maybe simply that the fact that the problem is tractable using mathematics that the human mind can create and comprehend. So, to summarize then, it may be the case that we can form the basis for the design argument with the unreasonable effectiveness of maths. In order to do that, though, we would need to show, first of all, that maths really is unreasonably effective, and secondly, that unreasonable efficacy is not due to physical necessity or chance. There are many applications of maths that are clearly not unreasonable or surprising, for example, phenomenological models or arithmetic. Maybe it's the beauty of maths that's surprising. Arguing against this would be the fact that the sorts of properties of maths that make it beautiful are exactly the same ones that you would expect to make it useful. But maybe in its favor is the idea that our own aesthetic sense matches with what's effective in maths. Maybe that's not what you would expect. Maybe it's the accuracy that's surprising. Arguing against that, you've got the fact that mathematics is infinitely flexible, but on the other hand, the laws didn't have to be mathematical in nature, so maybe there's a surprise there. In my own thinking, I'm at this point not entirely sure whether maths is unreasonably effective. I'm still debating this matter in my head. But let's say that it was unreasonably effective. How might a theistic Christian worldview accommodate that? Well, one way of doing that would be with what's known as divine conceptualism. This is the idea that mathematics originates in the mind and being of God. So if we think about maths as finding its source in God, then it's not surprising that he would create and sustain a universe according to mathematical principles. Similarly, if we're made in his image and we're formed via an evolutionary process which he guided, it's to be expected that we could discover and understand those mathematical principles. Thanks very much.
I wonder whether one thing that might be helpful would be to consider the opposite. So what would a universe be like if maths was not effective?
Yes.
And pursue that as a thought experiment. If you're still making your mind up, then perhaps trying to envisage a world where maths wasn't unreasonably effective, or where maths wasn't effective at all, might help guide you towards an answer. Is that something you're going to do, or you have been doing?
So it's a great point. I have done that a little bit. It's something that I think is valuable to do more. I mean, so you can imagine a universe where perhaps, so for example, you have a universe where different laws held at different points in time and space. So you might have a sort of like think of something like a sort of animist kind of viewpoint where there's different gods in different places and therefore different rules are followed in different places. If the universe was like that, then even if in each individual place in time and space it followed mathematical rules, it would be very hard to get a grasp of it. It's quite hard, though, to imagine what something would look like if it couldn't be formulated in maths. So I've been trying to think about that. I mean, it's certainly the case that with any model that we have, it's always an approximation. We never really know the ground truth. So a scientific theory is itself just an approximation to natural law. Natural law is the way the world really is, the way God governs it. A scientific theory is our human approximation to it. A mathematical model is then an attempt to encode that scientific theory in mathematical language. So, it's possible that the world is not mathematical, but it's just that we can approximate it with maths and that's good enough. That in itself is worthy of explanation, I think. It's hard to imagine what a world, given that we've grown up in one, it can be described mathematically. It's very hard to imagine what a world that wouldn't be like that would be like. I'm still struggling with that. If you've got any ideas, I'd be interested to hear them.
One last question. So I'm a computer scientist, so I'm going to mention Church, Turing, Gödel, who showed that maths can't be complete and sound. In other words, when you think it's beautiful, there are going to be mistakes in it.
So this is Gödel's incompleteness theorem you're talking about? You're talking about someone else?
Yes.
Same. Okay. Yes. I mean, I'm not. I think that's more applying, I guess, to a system, pure mathematics, where you've got a system of axioms and think you're trying to derive things logically from that.
Well, Gödel showed it applied to everything.
So
it applies to everything.
Okay.
It's one reason why computers have bugs, which we're all familiar with. You can't avoid them.
Okay, well, it's interesting. I haven't heard of the computer science example of this, but so yeah, I have to think more about that. But thanks, interesting point. I guess on a Christian worldview, you would expect things to be internally consistent. That God doesn't have conflicts within Himself. You'd expect Him to create a world that doesn't have those conflicts. But yeah, I'd have to think more about it.
Okay. So let's give a round of applause for all three panelists. Very interesting papers.